Having talked about breadth first search, we're going to now perform several examples of it just to see how it works. So we have a graph here. We're going to perform breadth first search starting at some vertex. I don't know, let's start at 1. Only because I don't really have access to nice colorings for gray and black, I'm going to color these things with red and blue. So I'm going to let blue mean I am currently trying to process that vertex, and red mean I am done with that vertex. The first thing that breadth first search does is it looks at everything adjacent to the first vertex. For our own purposes, let's try to keep track of what Q is, that thing that has all of the vertices in it. So Q starts with just 1. We then remove that, and Q becomes empty. Maybe we don't need to write that down. And we check everything adjacent to whatever we just pulled out of it. So we're going to check all of the vertices that are adjacent to 1. And we add all of those to the queue. Let's assume we just do that in numerical order. So 2, 3, 4, and 5. We then update some information about those vertices, though. We keep track of a parent pointer, which I will symbolize by a purple line between the vertices. So we now have this line that connects 2 back to 1. We have a similar line that connects 3 back to 1. Another line that connects 4 back to 1. And a final one, 5. So we have all of those parent pointers, and we also were storing information about the distance. So maybe in black, we'll write down the distances. 1 was 0 away. All of these were 1 away. And that's what we're going to do every time. Now that we've looked at everything adjacent to 1, it's the first thing that we processed. We switch its coloring to be red. So we're going to swap it from being colored in blue to being colored in red. Like I said, I'm using red here to symbolize I am finished. This is the black color in the code, and blue is used to symbolize gray. So now we look at the next thing in the queue. So starting from 2, we look at everything adjacent to 2. So we look at, let's do it again in numerical order. We look at 6, then 8. So our next queue is going to be 3, 4, 5, and then we added 6 and 8 at the end. So 2 gets removed, then we add our new stuff at the end. The distances for those vertices is going to be 1 more than what 2 was. We update the parent of each of them to be 2, because that's how we found it. So we draw in our edges. And then, now that we have found them, added them to the queue, colored them, and updated the distances, we are going to change the color of 2 to be red. We then repeat the same process for 3, 4, and 5. Now that we finished 3, we're going to try to do the same thing for 4, but notice 4 has no new adjacent vertices. So we don't do anything with 4. It just checks and sees, are the things next to me new vertices? None of them are, and just moves on with its life. So we're going to remove 4 from the queue and do no real new processing at that time. So we do Q equals 5, 6, 8, 7, and we update 4 to be red. We then go down to 5 and repeat the process. Having finished it for 5, we now repeat this process for every single other vertex in the graph. We'll sort of fast forward our way through this quick. All right, now that we've done a lot of these iterations, as a human, I now identify something, which is that everything left in my queue, 10, 12, and 13, for the vertices, are already discovered. They're just going to check the adjacent edges and then sort of fiddle out and do nothing. So at this point, when doing it by hand, I can definitely just say, all of those are going to finish up. I don't really care the order they finish up in, but they're all done with. At the end, notice everything is now colored in our discovered color, red, or in the code that would be black. And we now know, actually, the distance to every vertex. I realized I forgot to write down the distance to 12. It's going to be 4, 3 plus 1. We now know the actual minimum number of edges required to get to any vertex. There may be more than one way to do this. So for example, 7 can be reached in 2 ways. In 2, we can go 1, 3, 7 or 1, 4, 7. both of which go from 1 to 7 using 2 edges. And this thing we've created is called the breadth first spanning tree. It is actually a spanning tree within the graph that tells you the shortest number of edges from vertex 1 to every other vertex in the graph. This is a very useful thing if you're just trying to figure out quick ways to traverse a graph. So this is our first example. Some people will draw this as a tree afterwards, so I'll show you what that looks like if you want to see that. So we have 1 as the root, and then as children 2, 3, 4, and 5, they're all 1 away. 2, 3, 4, and 5. And 2 has 2 children, 6 and 8. 3 has 1 child, which is 7. 4 has no children, and 5 has 1 child, which is 11. 6 has 1 child, which is 9. 8 has 1 child, which is 10. 7 has no children. And 11 has 1 child, which is 13. And then we have one last node, which we haven't included, which I believe is 12, which is a child of 9. So then let's draw in all of our edges to draw the graph. So we have 1 is the root, and then there's this first child level, the second child level, third child level, and the last child level. So we can redraw this as a tree with the root being the starting vertex. So we have the starting vertex at the top here. And then this is maybe a better way to visualize how you can get from 1 to anywhere else. And the levels of this tree tell me information. The base level here says I'm at length 0. The level below that is that I'm at length 1. The level below that is that I'm at length 2. The level below that is that I'm at length 3. And the final level is that I'm at length 4. So it tells us a lot about the graph, it turns out. Some of these properties may be more useful in certain applications, but the idea that you can use this to fully explore the graph in an efficient manner and learn stuff about the graph is a worthwhile thing.